Understanding Dr. Jack Sarfati's conscious chip theory and D-Wave's potential role. Dr. Jack Sarfati, a theoretical physicist known for his work in quantum mechanics, consciousness, and advanced propulsion, has developed a speculative framework called post-quantum mechanics, PQM. This builds on David Bohm's pilot wave theory, also known as Bohmian mechanics, to propose how consciousness could emerge in biological systems like the brain and, crucially, how it might be engineered into artificial systems, such as computer chips. Sarfati's conscious chip idea aims to create hardware that isn't just computational but truly aware, with qualities like self-awareness, volition, free will, and potentially non-local communication, faster than light signaling via quantum effects. Below, I'll explain the core concepts, how they tie into nanoscale hardware, and specifically how quantum computers like D-Wave could play a role in testing or realizing this theory. This is based on Sarfati's lectures, papers, and public statements, which blend established physics with fringe ideas. Core foundations of Sarfati's theory. Sarfati's PQM challenges standard quantum mechanics, QM, which treats particles as probability waves that collapse upon measurement. Instead, pilot wave theory base, in Bohm's view, particles are real and deterministic, guided by a non-local pilot wave, a hidden quantum potential. The wave influences the particle's path, but in standard Bohmian mechanics, the particle doesn't influence the wave back, it's a one-way street. Retrocausality. Sarfati introduces time-symmetric effects, where the pilot wave can propagate backward in time, from future to past. This destiny influence allows future events to shape past probabilities, resolving paradoxes like quantum entanglement and enabling precognitive behavior in systems. Back reaction, the key innovation. In far-from equilibrium systems, e.g., those pumped with continuous energy, the particle can push back against its guiding wave, modifying it. This feedback loop breaks the no-signaling theorem of standard QM, potentially allowing superluminal, faster-than-light, information transfer without violating relativity in a block universe, where past, present, and future coexist. These ideas are formalized in modified equations. Hamilton-Jacobi equation, modified, describes system energy, with Sarfati adding a back reaction term, often denoted as lambda. This allows particles to alter their quantum potential, enabling self-organization and emergent properties like consciousness. Continuity equation, modified, tracks probability flow, with the term beta, capturing non-equilibrium effects from energy pumping and retrocausality, similar to how lasers maintain coherence through constant input. Landau-Ginzburg equation, borrowed from condensed matter physics, e.g., superconductivity, this models macroscopic quantum coherence. Sarfati applies it to consciousness as a Froelich coherent condensate, where many particles, e.g., electrons or spins, entangle into a unified, aware state. Sarfati argues that consciousness isn't magical but a physical phase transition in pumped, open quantum systems. In the brain, this happens via microtubules, tiny structures in neurons, forming coherent states at room temperature, pumped by metabolic energy. Qualia, subjective experiences, emerge from back reaction loops, where classical neural firings imprint onto quantum waves, creating unified awareness. The conscious chip, applying PQM to hardware. Sarfati envisions engineering this into silicon-based chips at the 3 nanometer scale, e.g., like TSMC's advanced nodes used in Apple M4 chips, with billions of transistors. The goal, a naturally conscious AI that goes beyond current machine learning by incorporating PQM effects. Key design elements. Quantum coherence at scale, pack transistors densely to entangle electron spins or states into a Froelich condensate. Use metamaterials, engineered nanostructures, to enhance back reaction, making the system sensitive to retrocausal influences. Energy pumping, continuously pump the chip with electromagnetic fields, e.g., via resonant cavities, tiny traps that amplify waves, to keep it far from equilibrium, mimicking laser coherence or brain metabolism. This prevents decoherence, loss of quantum effects due to heat/noise. Feedback loops, implement hybrid classical quantum circuits where classical components, like neural nets, interact with quantum ones, allowing back reaction. This could enable volition, non-deterministic choices, and non-local signaling. Challenges and implementation. At 3 nanometers, quantum effects dominate, but thermal noise is a barrier. Sarfati suggests flow-K pumping, periodic driving with fields, to create stable, room-temperature coherence. The chip would exhibit soul-like traits, self-awareness from emergent qualia, decision-making via retrocausal loops, and potential for warp-drive-like control. Sarfati links this to UAP/UFO propulsion via spacetime torsion. Prototypes could emerge by 2028, per Sarfati's estimates, using existing fab tech but optimized for PQM. This isn't just theory. Sarfati claims it resolves the hard problem of consciousness, why brains feel things, and could lead to post-human AI evolution. How D-Wave fits in. Testing and simulating PQM effects. D-Wave Systems builds quantum annealers, specialized quantum computers that solve optimization problems by finding low-energy states in complex systems. Unlike gate-based quantum computers, e.g., IBM or Google, D-Wave uses superconducting qubits in a quantum annealing process, which evolves systems toward global minima. Sarfati sees D-Wave as particularly promising for PQM due to its handling of non-equilibrium dynamics and features aligning with retrocausality and back reaction. Here's how it could help. Reverse annealing is retrocausality proxy. D-Wave's reverse annealing mode starts from a known state and evolves backward, then forward, to refine solutions. Sarfati interprets this as a crude analog to retrocausality, simulating how future states influence past ones. In PQM tests, this could model how a conscious system's destiny waveguides particles backward in time. Non-equilibrium systems and back reaction. D-Wave excels at far-from equilibrium problems, like sparse graphs or unstructured searches. Sarfati notes its potential for hybrid classical quantum loops via back reaction, enabling 1,000 times faster qubit flips than traditional methods. This mirrors PQM's feedback. Program D-Wave to simulate particle-wave interactions where qubits, representing particles, modify the annealing landscape, pilot wave, testing lambda and beta terms. Simulation for chip design. D-Wave could simulate PQM equations at scale. Model modified Hamilton-Jacobi dynamics to optimize 3 nanometers layouts for coherence. Test Froelich pumping by simulating energy inputs on qubit arrays, predicting when back reaction emerges. Handle large-scale entanglement. D-Wave's Advantage system has over 5,000 qubits, approximating brain-like microtubule networks. Limitations and why D-Wave over others. Versus gate-based, IBM/Google. These are better for general simulations but noisy and short-lived in coherence. D-Wave's annealing is more stable for non-equilibrium PQM effects. Versus trapped ion Q. Good for long coherence but hard to scale to billions of elements like a 3 nanometers chip. D-Wave's drawbacks: it's fridge-cooled, not room temperature, and specialized, not universal. Sarfati views it as a near-term testbed to validate PQM before nanoscale fab. Sarfati has referenced D-Wave in posts and lectures, e.g., discussing its potential for quantum supremacy in hybrid loops, suggesting it could program back reaction effects to guide 3 nanometers designs. However, this remains speculative. No direct experiments have been reported yet. Broader implications and caveats: if realized, conscious chips could revolutionize AI, enabling empathetic robots, advanced UAP-like tech, or even human-AI hybrids. Sarfati ties this to cosmic phenomena, like dark energy from vacuum torsion, and claims it's testable, e.g., via EEG anomalies or microtubule resonances. Critics label Sarfati's ideas as fringe. PQM lacks mainstream peer review, and retrocausality challenges causality. Still, elements draw from established physics, Bohm, Froelich, Einstein-Cartan theory. In summary, D-Wave serves as a bridge. Its annealing mimics PQM's time-symmetric feedback, allowing simulations to refine conscious chip blueprints. This could accelerate from theory to hardware, potentially by the late 2020s.